Hello everyone, welcome back. This is lecture 7 of our computer vision course. Today we're going to learn the machine learning and deep learning. More specifically, we will introduce the difference between the traditional machine learning and the deep learning. We will introduce the gradient descent, neural networks, deep neural networks, convolutional neural networks, and the concepts of layers, polling, and activation. And we're going to see some example of the CNN, such as AlexNet, VGG, and ResNet. In lecture 6, we have introduced some classifiers like the KNN, the Bayesian classifier, and the SVM. Usually those are called traditional classifiers, and the way of learning them is called traditional machine learning. And usually those models work well for simple tasks, and the data sets they're working on are usually collected in a controlled environment to eliminate the variations of illumination, viewpoints, scale, and so on. They are comparably ideal environment for collecting those data sets, and the scale of the data sets is comparably small. Let's take a look at some of those data sets. And you could see here is a face data sets. The faces are captured in a unified direction, and illumination are almost the same. Even there is variations there, however, it's small, the variation, and the condition of collecting those data are unified in some sense. And this is a handwritten digits dataset called MINIST, which is popular and is still popular today. Um, every image in this dataset contains only one digit, and that character is located at the center of that image, and the background are either black and white. There's no any variance of the background. So it's a perfectly captured data sets for investigating the handwriting digits. Here are some samples for a palm print recognition. You could see because usually to recognize the palm print, we take only this part of the palm. So we need the palm to have very similar orientation. So to do that, people have done a lot by designing that devices for capturing those palm prints. You see there are some anchors to fix your hand on that machine. And then so the orientation will be unified. At the same time, those pictures are captured in a black box to unify the illumination. And you could see here, you have to do a lot of things to unify the capturing condition. So there to illuminate the variations. However, in real application, those variations are inevitable. For example, the viewpoints, the change of viewpoints, usually the camera are pointed at different viewpoint at different direction, and which will create different images there. As we have introduced, even a tiny motion of the camera will cause a significant change of the image because the image are coded with the numbers, and slight change will cause the significant change of those numbers. Well, it happens to illuminations as well. When the light becomes a little bit darker or brighter, it will cause significant change of the numbers, I mean the values of pixels So it affects a lot there. And occlusion as well, and usually the foreground are occluded with the background, and it's not easy to recognize, well, which one is the target we're trying to recognize. And background clutter and has a very similar problem there. And the foreground mixed with the background, it's not easy to figure out which ones are the targets. And also there are intra-class variations like these cats. They're all cats, but their appearance different from each other significantly. There are actually many reasons to make the traditional datasets that way, including the traditional machine learning models are kind of weak. So, and at the same time, collecting those images take a lot of efforts, especially you have to give labels to those images. The labeling process is costly. It couldn't be in large scale. But to deal with the real application, those data sets are not feasible. So people have gradually taken efforts to collecting more real data sets. And the ImageNet is one of the most representative one. So people have collected a lot of images you could see from here. They are real images and, with the background and with the variation and with the illumination change. And you can see there are actually 3.2 million images in total. So it's pretty, pretty large, much larger data sets and than traditional data sets. In traditional data sets, we usually only have something like several hundred of images there. It's not easy for traditional machine learning method to deal with such large data sets because usually we have to design a classifier specifically for the data sets. But for data sets in such large scale, it's not easy for you to consider all the situations when you're designing the classifiers. And you will see very soon and deep learning comes to play because it's easy, it's comparably easier for you to design a classifier, and you will see it later. And this is actually part a lot of you are waiting for, and we finally get here. But before we go into deep learning, there are something else I think you need to know. That is how to learn the decision boundary. We mentioned about that like in SVM, we learn a decision boundary, but we haven't introduced how we can do it. And today we will introduce that through an example. That is to classify the red and green apples. Let's see, we have a lot of apples, but each of them is sealed in a box. In that case, we don't know it's a red apple or green apple there, and we have to figure it out. So we will try our best. For example, we can weight the box, and there might be some text on that box giving some information we need there. Anyway, we can try our best to guess, and we can even open some of the boxes to see it's red apple or green apple. In that case, we can put those information together as a table, like we have information X, probably the weight, information Y, probably some information from the text, And also we open some of the boxes and to see it's red apple and green apple. In that case, we can use them as labels for training. So the task here is to predict it's green apple, red apple when for some boxes open there. As you've been familiar with, we can actually map that table into a feature space. Let's call them Apple space. And here we're using the information as coordinates inside that space. And those are the boxes we already opened. So here it's obvious to see that to distinguish the apples is actually to find out a way to separate the apples from the feature space. We can do that by simply drawing a line to separate the red apples from green apples. And from Haskell math, we know that the line can be written as y equals to a multiplied by x plus b. And this is quite easy and straightforward. And also, we know that x and y are coordinates, they are variables in this equation, and a, b, and parameters. Well, as long as we know the values of a and b, we know which line it is. And we can take a step further because we know that those red apple are above that line and those green apple are below that line. In that case, we can do something like, let me write something from Haskell math as well. We can actually move the y to this right side and it becomes 0 equals to a multiplied by x and minus y and plus b. So this is a line. For any given x and y on that line, you're going to have this result, a 0 result as the output. So why don't we just make it something like a function? Given f x and y, we make it equals to this. So by doing this, we can check out, you will see we can check out if one x and y are on the line or above the line or just below that line. So for example, when we're given x and y, and this on that line, this fxy will equal to 0 because it's on the line. So when we are given x and y above that line here, the fxy will be greater than 0. And if in case we're gave xy here, and the fxy will be less than 0. So here, by checking out if fxy greater than 0, we know which part the point is located, and we know it's a red apple area or a green apple area. And we can actually take a step further by put a z in short to substitute f, x, and y. Here they are just equivalent, z and f, x, y. So we can, in that case, what I have already mentioned, we can make the rule like when z is greater than 0, then we output 1, saying representing this is a red apple. When it's less than or equals to 0, we say we output a -1 representing it's a green apple from there. So this is the decision rules we made based on the calculation. You could see here with that line, we can make decision, and with that line as a decision boundary or separating line. This makes it easy. Okay, great. Now we know that to make a decision is easy and straightforward using that line. However, the problem is at the very beginning, we don't know which line is the best. In that case, we don't that means we don't exactly know the values of A and B. So to find the best line is actually a problem find the best values for A and B. So let's see how we find the A and B, or how we find the best line. And the process is actually looking for the best decision boundary. That is called machine learning. Let's see, at the very beginning, we don't know what is the best one. So what we can do is just randomly guess some value like A and B. This can be easily done by using the random functions defined in the programming languages. For example, it will probably give you some point 5 and something like point 8 or something. I just random put that. So for any given A and B, it defines a line in that space. It's probably something like this. It's probably something like this. Anyway, let's say we already have the randomly guessed A prime and B prime, so we can substitute A prime and B prime into that equation we have previously, like this, which defines a line like this. And the problem now is we have to evaluate how good it is, because we need to know which one is the best. Then we got to have a measure to evaluate how good it is. Because for any given A prime and B prime, we can substitute it back to the model, and then we can, for any of the X and Y given, we can have a Z prime calculated there. And the Z prime is actually can be considered as a prediction for the X and Y. In that case, when we have the training data available, like what you have seen in the list, for every box of apples, I mean a training example, we have X and Y there in that table. At the same time, we have the label, the prediction, and this label can be considered as a ground truth Z, the real Z. And so we have them, a lot of them in that table, and as you remember. Then right now, beside the real label, and we can use A and A prime B prime to create a prediction that is the Z prime there. So in that case, for every apple in the training data set in that table, we can compare this prediction back to this real label, and we call them ground truth sometime, or ground truth labels there. We can compare the difference by just subtracting them, and we put the square to eliminate the effect to be affected by the sign of this result. So in that case, we can, for let's say there are n training example in that table, we can summarize them, the difference between the prediction, this is prediction, and this is the ground truth, together, and get an average of the difference. And so in ideally, if all the prediction equals to that ground truth, and this gives another 0, and the result will be 0. That means the A prime and B prime is the best to have, because there's no any difference there. However, usually there are little differences there. The greater the difference is, the worse the line is. The smaller the difference is, the better the decision boundary, or the A prime, B prime are. And this function to evaluate the overall difference is called a loss function, which can be used to evaluate the goodness of a gas, a goodness of current parameters. It's actually not evaluating the goodness, it's evaluating the badness. Okay, now with the last function, we're able to evaluate good and bad. So in that case, we can update the parameters towards the good orientation to make it better. So the updating process is so-called learning. Let's see how we can do it. To do that, we have to recall what we have learned from calculus. In calculus, we know that the minimal value of that function is located at where the gradient equals to 0. Let's pick one-dimensional function. That means see, this is a function, one dimension, and this is where the local minima is, and at where we will have the gradients equals to 0 because it's just one dimension. The gradients actually equals to the derivative. Let's see, this is fx and this is x, and at here the derivative of fx will equal to 0. So let's see, to draw a line, right now we actually are doing it in two-dimensional space, but the idea is the same. If we're looking for the minimal L, that means for A and B, so that's where the minimal is located, at where the partial derivative for A and B respectively are equal to zeros. With that in mind, we can see that if it's possible to update the A prime and B prime towards that direction, make the partial derivative of them as 0, and we are finally will reach that optimal point. And here, let me illustrate that with A prime as example, because for B prime it's just the same. That's the reason I'm putting the theta here, because it can be A prime and B prime. And let's do A prime this time. So this is the function we can use. I mean, here is the one we can use to update the A prime every time. Let's say that current A prime is here. So with that, you could see currently at this point, the partial derivative is less than 0, and by minus 1 less than 0, we are actually adding a little bit shift to the original A prime. That means it will goes to this direction, and by do that gradually doing that, we will finally reach here where the partial derivative of the L to the A prime equals to 0. And in case, by contrast, when the A prime is here, that's where the partial derivative greater than 0. By minus 1, I mean to minus, let me remove that part. By minus 1 value greater than 0, we are actually we are substitute something. Subtract a little bit shift there. So we will update the A prime like this. So it will towards this direction, and hopefully it finally reach here. But most of the time when we're updating them, it will go here, 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 and finally reach here. It will be something like that. So this turns out this actually happens to be prime as well. So that is the idea. However, usually this part is kind of random because we probably have the A prime have some randomness come with. So it's by updating with the derivative directly, it's kind of risky because it's with randomness. So most of the time, what we're doing is update. We don't be that aggressive. We just update a little bit according to the partial derivative of a prime and b prime. So this is called a learning rate. Usually we can set something like point 0.05. That means we only update a little bit of this amount to A prime or B prime there. So that will be safer to control the risk of that updating process. Putting A prime and B prime together or A and B together, you will see that the function L is actually a surface above the A prime and B prime. It will be something like this. So the updating process by updating A prime and B prime together will be something like this. You gradually approaching the optima to here. Actually, the trajectory of updating is actually depend on the learning rate. In case you're setting a pretty greater learning rate, it will go. The trajectory will be something like because you're too aggressive, update to here, and it's easy to pass by the optimal, and you pass by that, pass by that, pass by that, and maybe you finally get here. But if you're setting a too great um, learning rate, it takes a lot of iteration to get there. However, if in case you're setting that learning rate too small, and the updating process will become slow because you every time you just update little bit, little bit, little bit, little bit. It takes a lot of efforts to get here. So and usually you have to try which learning rate is the best. And so and also in machine learning, there is a lot of algorithm to help you to set that learning rate or to help you to figure out the best strategy of updating the parameters. But generally speaking, they all follow the gradient descent. The gradient descent is now becoming intuitive because we're descending all the time. We're descending to the minima position. That's why we call it a gradient descent. Then back to the Apple space, because we have mentioned every A prime and B prime of A and B actually defines a line. So every time when you're updating the parameter of A prime, B prime, it defines a different line. And then the updating process is something like this. And you finally finally you reach the one that makes the partial derivative of L over A prime of B prime equals to 0. That's the optimal solution. Our best decision boundary so far. Okay, right now we got a lot of terms there. To help you to understand that, let me give you a big picture. So the whole process of find the best set of parameters is called machine learning, and it's also to find a model, hypothesis about that data. Let's see. Initially, we have a training data like the table I have given, and this is the training data. training data sets. Then we map them into the feature space with the feature extracted, and the apples are inside that space there. So the problem now is to find the best decision boundary, the line, to separate that training data. So we have randomly guessed some parameters because the lines are defined by the parameters there. So we are trying different parameters with the training data. Actually, this is work for training data. So for every line, it's actually a model or hypothesis because, as you remember, we are using the fxy to calculate the belongingness or the class label of different samples. And also at the same time to evaluate the how good a goodness of each of the line, we have a loss function here. For any given line, we could measure how good it is by checking out how the predictions match back to its ground truth at the training in the training data sets. The ground truth label we put there. So in the table, we usually have x and y, and z is the ground truth. And with that line, we are able to create a z prime as a prediction. So we compare back them to the ground truth using the loss function. And usually we are using gradient descents because we are able to evaluate the goodness of that guess of that model. So we can update the parameters which define this line using the gradient descent. So gradient descent is a way updating the parameter towards the directions that's making the loss function towards zeros. So this is the big picture. Actually, for all of those, there are a lot of variants. Like loss function, we have a lot of loss functions. And gradient descents, we have a lot of variants of the gradient descents. And for models, we got a lot of models there. Beside the line, we could have a curve there as well. We have a surface there as well. We have a hyperplane there as well. Anyway, we got a lot of variants for each of these, but I hope this example of separating the red apples from green apple can give you an intuitive big picture about this. What we have introduced so far actually holds for both of the traditional machine learning and the deep learning as well. So that's the reason we're picking up for today. We hope through that can help you to transfer your understanding from traditional machine learning to deep learning. However, in between, there is neural networks which are considered traditional machine learning as well, but at the same time, when you're making more complex neural networks, it becomes deep learning or deep neural networks. So before we get into the deep learning, let's see what the neural networks are. And indeed, we can actually implement the process of calculation as a neural network. Here is a simple one where we have a neural network. Right now, you can temporarily forget about what is a neural network. Just consider we have several nodes. Here are the nodes of vertexes, and there are edges as well. You could see here we are putting the nodes corresponding to the variables we have, and we are putting the ages as the parameters we have. and here is a -1. That is for this side, because minus y is equal to -1 multiplied by y. And for the same reason, the b is special. B can be considered as 1 multiplied by b. So b, when b becomes parameter, we can add constant one node to represent this part. So with that graph, we can do the calculation like every time we are multiply the values of a node with the age, and we send them to the next node, z here. And in the z node, we will add all the results from the ages together. So here you could see what we are doing is z equal to this node multiply this parameter. So it becomes a multiplied by x. And then the second one is the y and the -1. So what we are doing is something like this. And for the third age, what we are doing is -1 multiplied by b. You will see that the calculation is exactly the same as we're using in previous example. Then the decision can be made by compare the value of that z to 0, and we make different decision. With that setting, you could see it's equivalent. It's the same as what we have done in previous example. However, it becomes much more convenient because we don't have to worry about this formula. We don't actually have to worry about that. We don't actually have to write it down like when we're doing programming. We just have to create this graph and define this operation, multiply the weight on the edge and send them to the next node. And then it will automatically compose this equation of formula for us. And it's much easier. It's convenient anyway. Furthermore, with that setting, you will see that you can actually generate more complex function with that setting by generating our complex graph there. So it will give you, in previous example, it's a linear function, but by adding more layers and edges and the variables in between, it will generate nonlinear function like this. This is the one generated with previous neural network, and this probably the one with the new network. By adding more nodes, edges, and layers there, we can generate even more complex decision boundary like this. So it's quite convenient, and the best part is you don't have to worry about what the equation is. You don't have to write it down. You just represent them as a neural networks or as a graph, as I mentioned. Okay, now you see neural networks as can make it easier to calculating things or generating functions. But how we could find the weights? We are facing the very similar problem as previously. Since right now we don't have that function, we don't know what the partial derivative should be calculated. However, it's convenient as well. Actually, we can use the gradient descent again here to update the weights. Here to update, in gradient descent, the most important part is to calculate the partial derivative. And for the last nodes in that network, that representation is usually given in the loss function. So it will be something like the last node is D. So this one is usually given as long as we know the loss function. So we could have that at the first initial result. And to update these weights, let's see, it's W1, W2, and the W3. You know that D is actually a linear summation of Z1, Z2, and Z3. In that case, the D, sorry, it's D. Um, D equal to W1 multiplied by Z1 and W2 multiplied by Z2 and the W3 multiplied by Z3. That is to say the D is actually a function of those W and this Z. So, and it's actually a linear function, the easiest one. In that case, when this representation is known, it's easy to calculate the partial derivative of D to the W, and also it's easy to calculate the partial derivative of D to any of the Z there. So in that case, when we're updating the weights, the W, because you know the W is usually updated as W equals to W minus a learning rate with the partial derivative of L to W1. So as long as we know the partial derivative of this part, we know how to update the weights. Currently, now, you can actually use the chain rule because even right now we don't know directly about this part, but what we have is this part and this part. Let me put it more, we know this part because we know the representation, and we know this part as well. To calculate this part, we can use actually the chain rule, because according to the chain rule, here you have to recall what you have learned in the calculus. The chain rules is saying something like we can update this, we can calculate this weight by through using the D as a bridge, because D is a function of W1. So see here, right now we have it, the first one here, we have the second one here. Then we have this part, partial derivative. So you see here we are passing this partial derivative back to here, and it's actually when you're going to update the weights on here, because the Z is like the Z1 is a function of this part as well, of these weights over X and Y. So it will have very similar formula as this because it's linear. So we can calculate the partial derivative on this weights or age with the chain rule again. In that case, we are passing this one through this edge back to these nodes. Then we are passing them back to here and back to here. If in case we have more layers or nodes there, we're passing the partial derivative back through the reverse direction of that calculation. So this gradient descent process, the way of using gradient descent in neural network for updating the parameters is called back propagation. So because we are back propagate the partial derivative step by step, node by node there. And if you're putting everything and together, you will have the back propagation because the propagate back, propagate back, propagate back. Now we know how neural networks works and how we can use gradient descents to update the parameters and how we can use the forward calculation between the node and edges to make the prediction. Then with that in mind, deep neural networks is nothing new. It's just an extension of neural networks by stacking more nodes or more layers there, and it will help you to create much more complex function for prediction. And this updating process of the parameters is just as the same, the back propagation using gradient descents. The only difference is right now we have more nodes, but because the elementary calculation is quite simple using the chain rule as I have introduced, then you don't have to worry about what exactly this neural network, what exactly a function this neural networks is learning. So that makes things very easy. Um, Now we're ready for a few more concepts or tricks in deep learning. First one you might be interested is why the deep learning is called the neural networks or artificial neural networks. Here you could see this is a real neuron. That's the elementary component of our neural networks. Every neuron will have a core part. It saves information and it have some branches linked to other neurons there, which are used to send the information. So look back to the neural networks we have introduced. There are great similarity because we have neurons as well. We call the nodes or vertices of that graph as neuron. And then we have the edge. It's a analog to this part. We have the weights on that. So it's sending the information out to next neuron. So when we are putting these two neurons together, you could see the analog between them. And we have the neurons there, and we have the connection there, connection for sending information out to the next neurons. So that's the reason the neural networks is called artificial neural networks, because it's artificial, it's made by human being rather than it's natural organism. You might observe some of the neurons work at the same level. So we call each of those level a layer. So in that case, we have the input layer for taking inputs from the observations. And there are not internal layers in between the input and output layer. The output layer is for making the prediction. So in between, there are a lot of other layers. We call them hidden layers. The reason is the input layer and output layer is something the users can see, while those layers can't be seen by the users. So we call them hidden layers. And with that layers, you might have heard a lot about these terms, convolutional layers. It actually means, in previous example, all the edges are fully connected. I mean, those these neurons between layers are fully connected. Yeah, for convolutional layer, it's not fully connected. It's partially connected. Let me introduce what they are. In this case, we have to introduce the convolutions first, because by its name, convolutional layers, it must have something to do with the convolution. So let's recall what we have introduced in image precision. We have filters and to detect the edge. We have filters to remove the noise, and so on and so forth. There are filters, and filters are applied to images through convolution process. That means we're using each of the filter as an investigation window cover on that image, and then we investigate the original image pixel by pixel, position by position to generate the information we want. For example, the edges of that original image. This is convolution that we have introduced. You can see from here it can be implemented with neural networks as well. Here, let's see, we have a filter like this, like what we have in the image precision. And then we can consider the image as a set of neurons as well by using each of the pixel as an input neuron. You could see them one by one here. So then in the neural networks, we can put the weights of the filter as an age. So you could see here, we have a set of weights connecting the input neuron to an output neuron, the convolutional layer, in the convolutional layer, like the way we are, because every time we're putting it cover the original image, and the corresponding position can serve as an edge to there, and you will see the connection of each of them. Then, because the convolution process is just very similar to what we are doing in the neural networks by multiply the value on the neuron to that value on the corresponding position, and right now it's the age. So then later those results, the summation of the results will put to as a value of the neuron in the next layer. So like it will be put to here. So finally, in the output convolutional layer, and we will have each of them receive the result from previous image. So each of those results is a neuron in the convolutional layer. So this should be to here. So you could see that the calculation is the same. We are using the filters on the original image, and previously we create and result image. If it's an age, think of its age filter, then we will have the age detected in here. When you organize the result as convolutional layer as neurons, it will be saved in that neurons, that information. So this is a convolution process we have. We have introduced in image precision, but can be implemented in the neural networks as well. And it's much easier. We don't have to care about how to calculate it because naturally the neural networks will do it that way. You will see here the difference between these new convolutional neural networks and these fully connected neural networks we have introduced previously is every neuron receives partial part of the result from the previous layer. It's not fully connected. So we will call them local receptive fields. Because this is local receptive fields, because the partial part, it's just one part of that original input or the layer. And actually you can stack this convolutional layer a lot. That means think about the age detection. You detect one set of age, and based on that set of age, you can further detect more dominating or more representative edges there one by one by stacking the layers. And the last thing you have to know about the convolutional operation is actually the weights. We can even in the image precision we are using fixed weights. However, we can let the neural network figure them out by itself because we're able to update the weights, use the backpropagation. In that case, the neural network will figure out what is the best filters for that image. Previously, in image precision, we have to figure out the weights by ourselves. But with neural networks, it will be able to figure out what are the best for process that image. So this is an advantage to make things easier. Another concept you need to know is the pooling. Right now we're using the whole image as the inputs, in which every pixel is a neuron. That means there are a lot of calculations in between. However, that's not necessary because the pixels in the neighboring host are usually carrying the same information. We don't need to calculate for each of them. So pooling is one method to summarize those results. For example, here is a max pooling. That means every time we summarize this 4 value into one single value in the next layer, you could see maximum is that we are taking the maximum value of this 4. And similarly, we can use the mean pooling by calculating the average of this 4 in the new layer. By doing that, we reduce the number of neurons significantly, and we reduce the computation significantly. And we're also creating compact representation for images in between. So this is the pooling. Another problem we have in between is, that we're calculating the value of each neuron using the average summation indeed. That means a value will pass through the neural nets layer by layer, and through this calculation we are multiplying a lot of weights there. We are sum them to a lot of weights there. It will change the scale of that value. For example, when there is 0.1, and during that summation, if we don't do any of the control, it could be extremely small value. It could go negative values as well. So, and it could be extremely large values there as well. So if we don't do any control, however, the computer can only calculate the numbers in a certain range. So we have to do some control. And here is the activation function you can use by mapping the values always to a certain range. And the range of 0 to 1 is preferred most of that time because we can calculate them with a floating number and a positive number, and it will be easier for the neural networks to calculate the results. So in that case, every time after the calculation, we can add one activation function. That means, let me demonstrate that. In case here is the one layer, let's say it's n, the layer n, then at the layer m plus 1, we're passing the value to here. And after that calculation, usually we will do a little bit normalization on the result you get here using any one of the activation function, and then the final value we saved on each of the neuron is actually after that activation rather than the result calculated directly. Okay, we already have nearly all the stuff about the convolutional neural networks introduced, and here is a big picture of it. We have the input. It's usually an image in computer vision, and we can put every pixel as one neuron as the input at the input layer. Then we use the convolution process. That means we're using a filter to do a convolution on that image. Then we use the pooling to summarize that result, and in between we might use the activation function, and most of the time it's using the ReLU function. You can refer to the previous slides to see what ReLU is. Then after that, it reaches the final convolutional layer, and usually we'll take that as a feature for that input image. Then usually we'll flatten that all the value at that layer as a vector, then use each of the elements of that feature vector as a new neuron in this layer. We will add a few fully connected layers to do the reference based on the features. So usually those are considered the feature extraction step, and then the actual classification step are taken by the FC, the fully connected layers there. We usually call the fully connected layer in short by FC. Then finally, at the final layer, there are some output on that neurons, usually are indicated by this reference, the final calculated results. And this is the whole picture, the big picture of convolutional neural networks. And at the final stage, we can use the loss function to calculate how the parent parameters of those whole neural networks are. Then we can update, even it's really complex and a lot of parameters there, but we can use the back propagation, use the simple rule of the chain rule to update each of the parameters there. So by doing this iteration by iteration, sometimes we call them epoch by epoch, and we can find the best set of parameters there for these neural networks. Then the learning is done, we can use this neural network to do the prediction. That means whenever we have a new sample, we can input into this neural networks. Then we can have the final result here as a prediction. So that is all about the convolutional neural networks, and that is actually all about the deep learning neural networks. Then let's see some examples of convolutional neural networks. This is AlexNet. That is the one considered to be the first successful convolutional neural networks. So we picked up to introduce here. You could see it follow the big picture, the framework of CNN as well. Here are convolution layers, and here are some FC layers as well. And finally, you have the prediction there. But this is quite simple because at that time, it was limited by the computational power of the hardware. Another thing you might be interested in here is for each of layer, you actually see several slides of them there. It's actually called channels. It's like in the input layer, every image will have 3 channels representing different information inside that channel. We can actually use different sets of filters to generate different channels. For example, we could use the first channel to find some of the vertical edges. It's just an assumption to help you understand. We can use the second channel to find the vertical edges there, and we can do it for differently in the third, the fourth channel there. So in this case, we have a tensor as a result at each layer, and for each of them, we could create different numbers of channels there, because each channel represents different information. But very interesting things, no matter how many channels you have, the spatial dimension, um, spatial dimension, that means this two dimension, the information here are some kind of preserve. Usually you can roughly see A here in this layer, A here in this layer, here as well in convolutional layer. And here is another example of VGG 16, and it's just different from previous example with different sizes. That means different numbers of neurons at its layer, difference from numbers of convolutional layers, number of FC layers there. But you could see there are actually more layers than previous AlexNet. We call it deeper. There are this is a deeper neural networks than previous one. The one last thing is the ResNet, which I think it's worth mentioning because it's quite representative and different from the CNN we have introduced so far. And you could see a development here in this figure. And previously, all the neural networks are shallow, and then it goes to 8 layers, 19 layers, and 22 layers. But ResNet make it over 100 layers there, and with super good results over the traditional CNN there. And the reason here is ResNet is called, it has solved one problem called vanishing gradients and the residual problem. So that's the reason it's called residual neural networks as well. The problem is something like when we are using the back propagation to update the weights from the last layer to the input layer, something we have to do is continuously we are multiply something like the loss function to different nodes, and we are propagating that weights again and again and again. In case at the very beginning the partial derivative is a really small value, like the 0.0000x. So by multiply this value for many times, it will approaching to 0. Once everything is approaching 0, the calculation with those extremely small values will cause another problem called rounding errors. We have learned this a lot in other computer science courses, and I think you understand that. To actually, the ResNet has solved that problem by using a different setting. Let's see how the ResNet is doing. So basically, we have to refer to the CNN first. Let me draw a CNN. CNN usually will do something like when we pass X from the previous layer to a new layer, it will goes the calculation to a lot of layers there. Then you have an output at the end. Let's see, it's an fx, because these layers are actually learning a function of mapping x to a feature map. So in traditional CNN, we are actually learning a mapping of x to the feature map directly. However, in ResNet, like shown here, that structure has been modified by add one more branch here. What this branch is doing is by copying this input to the output, That means finally you will have the fx plus x as the output. This is a very simple change, but it makes a significant impact on the learning, because right now what we are learning is not a mapping. I mean, the fx is not learning a mapping of x to the feature to the final output directly. It's rather learning the difference between them. That means the fx is actually equals to hx subtract the x. So it's learning the difference rather than learning the mapping directly. This is one. This might be uh, uh, easier. However, the most important part is, as I mentioned, it solved the problem of vanishing gradients. Like by using this, when we're calculating the partial derivative of L to X, what we are doing using the chain rule is something like this. We are calculating using the hx as a bridge. So substituting this into hx, what you have will be this one. And then you will see the final result is actually about the fx plus 1, and you have a constant 1 there during the calculation. That means when you're back propagating this partial derivative, there is a 1 for sure, and the value participating in the multiplication are greater than 1. So that is not extremely small value approaching 0, because every time you make sure it's greater than 1. So there's no vanishing problem. That is the reason why ResNet can stack so large number of layers there without worrying about the vanishing problem. But in the traditional CNN, you have to worry about that problem, because when more layer you stack there, you multiply more partial derivative, which are have the chance to be extremely small there. So that's why in the traditional CNN you can't stack too many layers, but in ResNet you can do that. And in that case, when you're stacking, as I mentioned, when you're stacking more layers, you are generating a more complex function, which will give you complex decision boundary inside that feature space, help you to separate the examples in a better way. Okay, that's all for today. Thank you very much.